Alright. I want to outline for you these notes that I've given to you in class about exponential growth and decay. Now, for those of you who don't remember what we discussed, this is just an overview of that. Now, exponential growth and decay describe a lot of processes that we see in, how you say, the real world, or that we see on a daily basis. Now, we don't think about them in depth as much as some people do. However, it's very helpful to know. It's very helpful to kind of dive in a little bit deeper and think about something deep for a change, whereas you only think about it on a surface level. Alright, so to fill out these notes, I want you first to know this. I'm going to start with B, because you need to know what is the standard equation for exponential growth and decay. Standard equation is y equals a, that's our coefficient, b, that's the base to our exponential, or our exponent portion of this formula. So y equals a times b to the x power. Now b is the only thing raised to that exponential power. Often, the rate of growth or decay is represented as a percentage. Like the ozone decays at 3% a day. That's a little extreme. That's probably not even true. However, you hear these percentages that come out. I'm getting 5% interest on my investment in the bank every year. That's not true either. I wish it were. Or you pay 5% interest on your mortgage. That could be a little bit more true. So, rate of growth and decay are often represented as percentages. So the key to working with them mathematically, because we cannot multiply percentages, or at least they don't make nearly as much sense yet. So we're going to change these percentages into a decimal form. Alright, so, and here's a note. The way to change a percentage to a decimal, to change a percent to a decimal, all you have to do is divide by 100. Okay, a percent is a fraction out of 100, hence it's called a percent. Cent has Latin roots to centennial, or century, or centurion. So a captain of 100 people, or a piece of 100, which is in a dollar, which is why we call them cents. But per cent is per 100. So anyway, if I give you 13%, that is out of 100, which would equate to 13 hundredths. Okay, so if you want to change a percent to decimals, simply divide it by 100. Okay, now notice the variables here, y, a, b, and x. Okay, we need to define those. So y is going to be the total after we've gone through this process. Or, in other words, it's the end result after a certain period, either a period of time or a certain number of how many processes happens. Okay, so the end result after a certain period. Okay, A is going to be our starting value. Okay, so this is the end result after the periods have occurred. A is our starting value. Now R is kind of interesting here. There's a B here, not an R. That is not coincidence. That is intentional. So let's go ahead and define R. It'll come in handy in a moment. R is our rate of change. Whether that's growth or decay, it doesn't matter. It's still the rate of change. And X, that is the number of periods. So for instance, if I get 5% interest in my bank every year, after 5 years, that's 5 periods. So that's how X works Now let's get back to this B business. Now B is not the rate, okay? So the way we calculate B, there is some explanation behind why this is, but for time's sake and for all intents and purposes, B describes either 1 plus the rate, or it describes 1 minus the rate, okay? So for exponential growth, it would be 1 plus the rate. And for exponential decay, it would be 1 minus the rate, okay? Now, again, for time purposes, I'm not going to go into depth about different words to represent growth and decay. We're just going to simply put increasing for growth and decreasing for decay. Because if something is decaying, it's disappearing essentially, or dissolving. Growth, if it's increasing, it's growing. Or generally speaking, that's how it's viewed. So we're going to take the information that we've developed here and we're going to apply it to a practice problem down here. Alright? So, in this particular practice problem, here's the situation. In the year 1990, Florida's population was 13 million. The population was increasing at a rate of 1.7% each year. So we need to write a function that represents Florida's population growth since 1990. Then we're going to use that function to predict the population in 2018. Now there's a lot of things going on here. Fortunately, we have a little breakdown going on. So with this breakdown, we're going to try to keep this pretty simple and pretty easy. First things first, we need to write an equation. Our equation is going to be of the same form that that most exponential growth and decay equations are. Alright, so y equals a, b, x. So we need to figure out what all these components are, and we're going to do that as such. Y is the total population of Florida in a given year. That's defined for us. We don't need to really worry about that just yet. A is a starting amount. Well, we're starting with 13 million. They don't care about writing all the zeros, we won't either, but it's 13 million. The growth factor is 1.7% each year. And like we said earlier, we don't want to work with percents. We want it to be in a decimal form. So we're going to divide 1.7 by 100. So if I can do that by hand. 1.7 divided by 100, and that would get me 17,000. Alright, so this is, or 0.017. Okay. Then the number of years since 1990, we can go ahead and calculate that. 2018, from 1990 to 2018, that's going to be 28 years. Alright, so that's going to be helpful in the moment. Now, we need to construct this formula. So far, what do we have? Well, we don't know the value of y, but we have y. A is 13, that's our starting value, right? Starting value. B, well, we haven't really figured out B, and all we have is really r. Well, we're going to go back to what we talked about for exponential growth. B is 1 plus r. So I'm going to write down here, B is 1 plus r. Well, I know what the r is. R is this 0.017. So B is 1 plus 0.017. Simplified, B is 1.017. So I'm going to substitute that into our formula now that we have it. And our exponential value is x at this point. So y equals 13, 1.017 x. Now we need to know the population in 2018. So I'm going to use our exponent here, which is 28 years, and solve that. So it's 13 times 1.017 to the 28th power. Now I'm going to put that in my calculator. Remember, this is an exponent, so you can not simply multiply 1.017 times 28. That doesn't work. But once you plug it in properly, you should get 20.8, and this is in millions of people. Alright, and so that would be our final result. Okay, so try to use these notes to guide you in your work, and refer back to them as you need to. Okay.